Hi everyone, welcome back. Today we're going to look at graphs or network data. So graphs are everywhere. For example, for the internet is a 50 billion web page network, where each web page is a node in the network and an edge is a web link connecting two web pages. Another example is the Facebook social network, where it has over 2 billion users, where each node in the graph is a user and each edge is a friendship link. There are actually a lot more examples like these. For example, Twitter is a who follows whom graph. Amazon is a who buys what graph. So for Amazon, we normally don't think of it as a graph. But if you can think about how to connect a customer with the products that has purchased, then we'll have a bipartite who buys what graph. In other domains like telecommunication, we can also have a graph. For example, we can have a cell phone network, who calls whom. And in biology, we have protein-protein interaction networks. To analyze graphs, we first need to know how to represent them conceptually, visually, and programmatically. The most natural way to understand a graph is as a node link diagram, as shown at the top left corner. Here we have 4 nodes. The edges connecting them may be weighted, and we usually use edge thickness to encode edge weight. A thicker edge means heavier weight, and the edges may also be directed, and we usually add an arrow to the edge to indicate the edge direction. An adjacency list is another way to represent a graph, where we have the nodes as the columns and also the rows. For example, here we see that there's an edge going from 1 to 3. So then for row number 1, we have the number 3 at the cell 1, 3. So meaning there's an edge of weight 3 connecting node 1 to a target node 3. So you notice that this is not a very space-efficient way to store a graph, because you also need to store a lot of zeros. So zeros here means there's no edge. So a more compact way would be like an adjacency list, where for each node, we only keep the target node that it's connected to. For example, at the top right here, we see for node 1 is only connected to node 2 and 3, so only store the node ID 2 and 3. So adjacency list is compact, but it's not the most common distribution format. The most common is actually an edge list, where each edge is represented a row in the file, and we have the source node, target node, and optionally the edge weight. So it's most common because this is also what we call a comma separator file or a CSV file. And however, being most common doesn't necessarily mean it's most easy to work with. Most of the time it is, but sometimes it can be painful. For example, if the node or the edges have many attributes or columns, then it can be painful to parse them. For example, if you have, say, a lot of node attributes that have text, or let's say the node name included, then you may need to parse double quotes or single quotes, and that can be painful. So you notice that for the nodes, often they are identified by their numerical IDs. So you may ask why. The main reason is because nodes often appear many, many times in edges. For example, in a billion edge graph, a node can easily appear like tens of thousands of times. So if you don't represent each node as by its node ID, then you will need to repeat that node name, for example, many, many times. And imagine that it's a very long node name, then it will be not very space efficient. So this is why we want to represent each node as a node ID. So then the question is, how do we assign node IDs to the nodes? So for small graphs, it can be pretty simple. But imagine this is a billion node graph, then it can be pretty computationally heavy. And also, you may even run out of RAM, right? For example, you will need to store the mapping of node name to node ID. So in Java, you might use a map. In Python, you may use dictionary. And imagine having a billion entries, so you can run out of RAM. So how do we do this easily? So of course, as we mentioned, we can do it programmatically. Or my favorite way is actually using SQLite. So we'll look at an example of how to do that. So all of these techniques are doing the same thing. So essentially applying the same concept, which is that for every node or every entity in the graph, such as a person that we have never seen before, we want to identify or assign a number to it. So here's an example of how to use SQLite to assign node IDs. So this is my favorite way to assign node IDs, because everything can be done using simple SQL without writing complex code. So the first step is that we'll create an empty table, say with a column called name, to store node names. Second step is to create an index on that column so that we can quickly check for duplicate node names. The third step then is to just keep inserting node names into that column, and duplicate node names will be automatically ignored. And each node's ID can be retrieved by just getting the hidden row ID column associated with the row for the node. And row ID is a hidden column that SQLite uses internally to identify rows. And here we service that or use it to identify nodes instead. And lastly, once you have the node name to node ID mapping, then you can easily convert an edge list that consists of node names into an edge list of node IDs by using a simple join statement. So now that we know how to represent node IDs or a graph, so how do we store the graphs? So there are different ways. So if the graph is not that large, then you can store it on your own computer, for example, using SQLite. Or you can use a graph database, say Neo4j. And on a server, if you use relational databases, again, you can use the more scalable ones like MySQL or Postgres. And Neo4j, for example, now also support server deployment. And if your graph exceeds the space of a single machine, then you will need to use a cluster of machines. And there are also multiple ways. For example, if you need real-time read and write of graphs, nodes and edges, for example, then you may want to consider Titan, which is built on top of HBase, or the alternative S2 graph. And if batch processing is fine, meaning you don't need real-time read and write, then you can use traditional Hadoop. You can say, for example, the graph as an adjacency list or an edge list. There are also other libraries like Hammer, Giraffe, and they are both inspired by Google's Prego project. And also from other commercial companies like Twitter, they also have their own database, for example, FluxDB from Twitter. So in my research group, we like to use SQLite. And the reason that we use it is because it's great for our use cases. It can easily handle gigabytes of data. And usually that translates into about tens of millions of nodes and edges. And usually that's already a pretty good size. Of course, if you want to handle billion edges, then you will need to use a cluster-based deployment. Another benefit is that SQLite is very easy to maintain. So this basically all the benefits that you would get for SQLite, you would also get it here. So very easy to maintain, and you have just one cross-platform file that can be used in all platforms, like Windows, Mac, or even iPad. And also have a lot of language support. So you can write programs using different languages, using different APIs. And doing queries on the graph is also easy. For example, we'll look at an example very shortly, which is to just use one SQL statement, and you can find all node degrees. Another bonus is that SQLite supports full-text search. So if we want to, say, find particular nodes with a node name, you can easily do that using full-text search, which is built into SQLite. So if you do choose to use SQLite to store graphs, so here is probably the simplest schema that you may be able to use, which is just having a table called edges, and you store the source node ID in one column and the target node ID in the other column. However, you may sometimes want to also store node information, and also for edges, you may want to store, let's say, the edge weight, timestamp, and so on. Then you may need to use more tables. For example, you may want to have one called nodes, and it has 3 columns. One is the node ID, and the other is, let's say, node type. You can store it as integer or anything you want, actually, and also the node names. And similarly for edges, you may also extend our previous design to also store the edge type, edge weight, and timestamps. Here, notice that for the nodes table, we may want to make the node ID at what we call integer primary key. So integer primary key meaning unique. You'll make it as the unique index, and also that's how you identify each node. In this video, we look at how to store graphs and how to represent graphs.